Okay guys, we're going to do 3.1 average rate of change, also known as secant lines. Okay, first off, how do you find the average velocity? Well, you need to go back to your physics days for this. It's not too difficult, it's just the velocity is equal to total distance divided by the total time. So it's going to be the change in distance divided by the change in time. Okay, so write that formula down and we're going to use it here pretty soon. Okay, here we go. A ball is thrown off a roof and its vertical distance is given by the function this. Okay, so if you type anything here, it will tell you where it is in terms of distance, how many feet is the distance that it's traveled. Where t is represented in seconds and x of t is represented in feet. Okay, how far does the ball fall during the time interval 2 to 3 seconds? Okay, so we just want to figure out how far it went. So we need to figure out where the position is at 2. So we need to plug in 2. We need to figure out where the position is at 3. Plug in 3. And if we subtract them, that'll tell us how far it fell from the interval 2 to 3. So let's write this mathematically here. Oh, here we go. Sorry. I was trying to get my pen working out here. Okay, here we go. Okay, so if we want to figure out how far it fell from 2 to 3, what we were saying is we need to figure out the position at 3 and subtract it from the position at 2. Yeah? So we just need to plug in 3, so 16, 3 squared minus 16, 2 squared equals. Now we got to figure out what this comes out to be and what this comes out to be. I want to show you something on the calculator, so go grab one if you are watching this in class, and let me show you how to use it. I'll probably have to rewrite this up in a second. Okay, first off, this is our calculator here. First, go to the calculator function. I want to type in this function we have, x of t is equal to 16t squared. First thing I'm going to do is just type in 16 times t squared. Okay, that's my function. What I want to do is I want to store it in the calculator. This is going to make your life so much easier when the problems are more difficult. This one's kind of an easy one. But we're going to press Control var. That's the store button. Notice how it says STO on the top? That stands for store. We can call it whatever we want. I'm going to call it what I used on the PowerPoint, x of t. I'm going to press Enter. It should say done, that it has saved what it was that I wanted it to save. Okay, I wanted to plug in 3 into this and 2. So check this out. It's going to make my life easy. X of 3 minus x of 2. Press Enter, and I got myself 80 feet is the distance it traveled from the time interval 2 to 3. Cool? Okay, so let's type that in here and get ourselves our answer. So, get back onto my fancy pen. Okay, so x of 3 minus x of 2 equals 80 feet is how far it traveled. Okay, then it says find, or what is the average velocity of the ball during that same time interval? Okay, well remember average velocity is the distance. So velocity is equal to distance over time. Okay, well the distance it traveled was 80 feet, right? Divided by the amount of time we had, which was 1 second. From 2 to 3 was 1 second that passed by, which that would be 80 feet per, and remember the bottom was measured in seconds. Yeah? Now, notice what this would have looked like if we would have written it out in a function. It would have been x of 3 minus x of 2 all over, and that numerator would have come out to 80, right? That's what we said. All divided by the time minus the initial time. Yeah? And that comes out to 80 divided by 1, which is our answer. Okay, that is something we're going to be using a lot. That is the average rate of change formula, and I will be I wrote it down for you guys to copy down in just a couple slides. So let's go forward. Okay, what if instead of average velocity we wanted to find the velocity instantly at 2? Okay, so this is what Isaac Newton was asking himself. He said, I don't want an average velocity like we were doing here Here we were just looking at what was the average velocity it was from 2 to 3. He said, I don't want that. What I want is I want the actual velocity at 2. Well, how are we going to figure out the instantaneous velocity exactly at 2? Well, you could pick values that are closer to 2, like 2 and 2.5. That's going to bring you in closer to what it is that you want, right? So let's do that real quick. Okay, so we're going to do x of 2.5. This is very similar. This is the same thing we were doing on that last slide, right? X of 2, distance divided by time. 2.5 minus 2. I don't know what this is going to be, so let's go back to that calculator. And you know what? Why don't we write this one down as well before we go to the calculator, and we can just type both of them in. X of 2.1. Notice I'm doing the larger number minus the smaller number, all over 2.1 minus 2. Okay, and then now I have saved the x of function into the calculator, but remember that x of function is 16 times t, which is going to be your time, 2.5 squared, minus 16 times 2 squared, all divided by 0.5, right? We're going to figure out what this is going to be. This is going to be closer to the actual velocity at 2, yeah? So let's figure out what it comes out to. Let's use our calculator here. Oh, whoops. That was a mistake. Okay, we are going to do control divide so we can set this up. We're going to do x of 2.5 minus x of 2 all over 2.5 minus 2. So look at that. If you start zooming in on 2 like we did here, you get 72 feet per second is our speed there. Let's do it if we get even closer. So let's do control divide to set up our fraction. X of 2.1 minus x of 2 all over 2.1 minus 2. Okay, this is even closer, right? And what could we do to even get closer to the average velocity, or the actual velocity at 2? Because right now these are average velocities, right? For values. We could even get closer if we wanted to. Let's grab this function up here, press enter on it. Look, I can even put zeros here. That is even closer to the value of the actual velocity at 2. Let's see what it comes out to. And notice how we're getting really close as we get smaller and smaller values. We're getting really close to the actual velocity at 2. Okay, so this is what you would call estimating the instantaneous velocity. Okay, I'm going to write these two answers down on the other one, 72 and 65.6. 72 and 65.6. Okay. Get this to work here. It's giving me problems. Okay. So this one was 72 feet per second. The other one was 65.6, I believe is what it was, feet per second. Okay. And these are estimations for the actual velocity at 2, yeah? A way to write that is estimation for the instantaneous rate of change. That's what IROC stands for, instantaneous rate of change, at t equals 2, because we were kind of zooming in on values close to 2. Okay, let's go forward. Okay, notice here it's the exact same function. A ball is thrown off a roof and its vertical distance is given by 16t squared, where t represents the seconds and x represents in feet. Estimate the instantaneous velocity of the ball at 3. Okay, we're trying to find the instantaneous velocity. That means we're still doing an average rate of change. It's an instant. We're estimating the instantaneous. Okay, so we're trying to do it at 3. So we're going to be doing x of, pick a number really close to 3, 3.1, minus x of 3, all over 3.1 minus 3. That's going to give us an estimation for the instantaneous rate of change. And I can just type that into the calculator, and it'll tell me what the estimation for the instantaneous rate of change is. So let's do that real quick. Control, divide, x of 3.1 minus x of 3, all over 3.1 minus 3. 97.6 feet per second. Okay. 97.6, I believe it was. 97.6 feet per second. Okay, is the estimation for the instantaneous rate of change. Okay, let's go forward. So, whenever you see the word average rate of change, okay, average rate of change, estimate the instantaneous rate of change, or slope of a secant line, and I will explain that last one here in a bit. If you see any one of those three things, any one of these three things, write this down. You are doing the average velocity formula, which is what we were just doing right now, yeah? On that last one, we did x of 3.1 minus x of 3 all over 3.1 minus 3. Okay, 3.1 is our b value, our larger value, and 3 is our smaller value, and our function f in this case was x equals 16t squared. Yeah? So this is what you're going to write down whenever you see any one of these terms: average rate of change, estimate instantaneous rate of change, slope of a secant line. You automatically write this. Okay, let's go forward. Okay, that last one I said slope of a secant line. So slope of a secant line is the exact same thing as average rate of change. Secant line is something that cuts through a graph at 2 points. So there's 1 point, 2 points. Finding that slope, you would do y2, going back to our old days, minus y1 all over x2 minus x1. That's rise over run, right? Well, notice what it's doing. Y, another way of saying y, is f of x2 minus f of x1. That's the same thing as y2 minus y1 all over x2 minus x1. And we can rename our x's. We could just call this f of b minus f of a all over b minus a. Look at that. That is the same formula I just told you guys. Slope of a secant line can be found by this. You just get your y value minus your other y value divided by the change in x. Okay, now what we're going to be trying to do in this entire calculus class is, instead of doing averages like you guys have been doing for years, we're going to be doing things called instantaneous rate of change, where it only cuts through the graph at 1 point. It just touches it. This is called instantaneous rate of change, and we call that a tangent line, okay? And that's what we'll be doing in tomorrow's lesson, finding tangent lines. Okay, let's just do a couple examples here and you'll be good to go. Okay, I'm not going to actually solve these all out. I will just show you what you should be typing into the calculator here. Find the average rate of change of the function f of x between the two x values 1 and 3. Okay, I saw the word average rate of change. That means I immediately write this down. Yeah? Okay, now we just need to determine what's our function. In this case, our function is this. This is our f of x. And what is b and a? Okay, well, here's b, the larger x value. Here's a, the smaller x value. So we're going to do f of 3 minus f of 1 all over 3 minus 1. Okay, you just type that into the calculator. Store this function, type this into the calculator, and get yourself an answer. That's going to be your average rate of change. Find the slope of the secant line between 0 and 1. Now guys, there's the key words again. Slope of a secant line. When you see that, you automatically write this down. We're still using the same function, and we're doing it for the values 0 to 1, a to b. So we'd be doing f of 1 minus f of 0 all over 1 minus 0. Yeah, and it's going to come out to some answer. That's going to be your answer for the slope of the secant line. Estimate the instantaneous rate of change. There's the other way of writing what you need to see when you write this: f of b minus f of a all over b minus a. And we need our a and our b. Now, if you notice, it's only going to tell you one value when you do instantaneous rate of change, but we're estimating it. So you need to pick a value. This is going to be your a. You need to pick a value that's really close to it. 2.1. That'll be my b. Okay, now we got it. F of 2.1 minus f of 2 all over 2.1 minus 2. You're going to get some value. That's going to be a very close estimate to the instantaneous rate of change at 2. Now, it's still going to be an average, because remember, this formula is for average rate of change, but it's going to be close to the instantaneous rate of change because we picked values so close to 2. Okay, I got one more for you guys. Okay, we've done it by a graph now. We've done it by functions. Now I just need to show you how to do it on a table. Find the average rate of change. There you go. There's those key words again. Average rate of change. F of b minus f of a all over b minus a. For the slope of the secant line for the time interval 2 to 8, okay, we're going to be doing f of 8 minus f of 2 all over 8 minus 2. That's my a, that's my b. Okay, and then here, these are even easier because your function is given on this table here. F of 8 is 83 minus f of 2, which is 56, all over 8 minus 2, which is 6, right? So now, all you need to do is simplify that. So 83 minus 56 is going to be 27. 27 over 6. And we got ourselves an answer, because that won't, well, we could simplify it a little bit, right? We could divide each thing by 3. So if you divide each thing by 3, we're going to end up with 9 over 3. I mean, 9 over 2, sorry. Bad simplification. 9 over 2, and that's going to be our average rate of change, or the slope of a secant line, or an estimate for the instantaneous rate of change for some value in between 2 and 8, yeah? That's going to be those 3 things. Those are 3 ways to say it. Okay, and that's everything for this one.